tonight we are going to see some examples of functions and their graphs. Of course, there are infinitely many examples of functions, but some are more important than others. And the examples are going to gradually be more and more complicated. The first few are going to be quite simple. So the first one is the identity function on R, and it's defined like this: the real function f from R to R given by or defined by this rule, this formula, f of x equal to x is called the identity function on R. We say on R because you can similarly define identity functions on other sets. We are, however, not going to consider those things because we will mostly be considering only real functions or real valued functions. You remember, a real valued function is a function whose outputs are real numbers. And a real function is a function whose outputs are real numbers and inputs are also real numbers. That does not, of course, necessarily mean that the domain and codomain have to be R, just that they have to both be a subset, both of them have to be subsets of the set of real numbers. So this is the identity function on R is a real function. That's why we have written real function. Now, what are its domain and range? Clearly, the domain, or let me write at once, okay, instead of writing domain and then range. The domain and range of f are both R. The domain is the set of all first coordinates of the ordered pairs, which is whose collection is the set F, and the range is the set of all second coordinates. Now, if you look at the relation, the rule that defines this function, and you try to write F as a set of ordered pairs, how will it look? It's going to look like this. Right? Because here you should write f of x, but that according to this rule is nothing but x. So the set of all first coordinates is domain, which in fact is just R because there is no restriction on which real numbers you can take as the first coordinate or first component of these ordered pairs. Any x you can take from R. Similarly, as second coordinates or second components of all these elements, all these ordered pairs in F, all the real numbers appear. That's why both the domain as well as the range of F are R. Alright. Now next comes the graph of this. You have probably means you have definitely already seen graphs of such functions, not just this one, but again we are going to look at the graph. Now what do you do while trying to draw the graph of a function? You make a small table of values, right? So let's do that for this one. A small table of input values and corresponding output values. I won't take many points though, I will just take say 4 points. Say in the first row I put the x values, and in the second row I will put the fx values. Let me just take as x value first minus 2. Since fx is nothing but x, so the f of x, I am saying fx, but actually that's not how we should say it. We should say f of x. That is the value of the function at the input x. If it is minus 1 though, then this one is also minus 1. When it is 0, it is 0. When it's 1, it's 1. Now if we plot these points in the plane where you have chosen a system of x and y axis, I am going to do it not very accurately, okay, I am going to do it roughly. The thing is that if you are asked to draw a graph, of course you have to do all the things. You have to plot the points after choosing x and y axis, and then after choosing the axis you have to mark out the numbers on the axis accurately. But here I am just trying to show the general shape of the graph. So say this is my 1 and this is say 2, although we don't have 2 here. If you want, you can put one more place for 2, and this of course is 0, and then you have minus 1, minus 2. On the y-axis also correspondingly you have 1, 2, say minus 1, minus 2. You can see how carelessly I am just putting these points on the axis. So that's enough for our purpose. So one of the points is 0, 0. So this is the point 0, 0. And then we also have 1, 1. So 1, 1. And we also have 2, 2. Then minus 1, minus 1. Minus 2, minus 2. And when one joins these points, they are not going to lie on a line, I mean in this drawing, because I have done it so carelessly, but you can imagine that if you do it correctly, they will all lie on a straight line. And that straight line is the graph of this function, which is a straight line that passes through this origin and is equally inclined to both the x as well as the y axis, which is why this angle is 45 degree, and that angle is also 45 degree because the entire thing is a right angle. So this is the graph of your identity function. Or if you denote the output values fx by y, then you can even write this equation for the line y equal to x. Then next we have constant function. Unlike the identity function on R, which is unique, there is only one identity function on R. There are many constant functions. And that's why we write constant functions. Let C be some fixed real number. C is arbitrary. You can take any real number in place of C, but once you choose such a C, it is fixed. It's not going to change once chosen. The function f from R to R. So all these are real functions given by f of x equal to C is called the constant function determined by C. Or you can simply say that it is a constant function, because C is your choice, so you can choose different values of C. Say in place of C you can take suppose 1 or 2, but once you make that choice, then that will not change when x changes. Oh, and one more thing, when we write a function like this, the input x is always supposed to come from the first set, which is the domain of your function. So if you want, you can extend this by writing f of x equal to C, where x belongs to R, but actually there is no need to write that extra part where x belongs to R. It's understood that x has to come from R only, and that is why the first set is always the domain of the function. Now what are the domain and range of this function? Domain, of course, for a general relation, the domain is not always the first set. It can be a smaller subset of the first set. And in fact, the domain is nothing but the set of those points in the first set from which arrows are going out. It's the condition that a function has to satisfy which makes the first set its domain, because for a function, all the elements of the first set should contribute to the arrows. No idle element should lie here. You can, however, have idle elements here. That's a different matter. Okay. So the domain here also is R, just like the identity function, but the range is not R. Clearly, the domain is R, but the range is nothing but the set of all outputs. The domain is the set of all inputs. Here the only output is C. No matter what your input x is, the only output is C. And that is why the range is the singleton set C. Oh, and one more thing I completely forgot. Have we seen, or have you seen carefully whether these really are functions? In other words, is every input giving us a unique output? See, that should always be there. Otherwise, it's not a function. It's a general relation. In case of the identity function, what was the rule? The rule was this. This was the function with domain and codomain, and the rule was this. The first thing you have to see is whether you can take any element from the domain and put in this formula so that the formula makes sense. Is there any problem in taking a real number x here? No, you can just take any x and put it here in this formula. That does not cause any problem. That means, yes, R is the domain. In other words, every real number is able to be an input for this function. And when you choose an input x, what is the output? The output is also x, and at the same time nothing else. So for every input there is only one and only one output, and that is why this is indeed a function. It's not that for a given x you are getting 2 or 3 outputs. No, that is not happening. Each soldier is attacking only one soldier. So everything is okay. This is the function. What about this formula though? Here also there is no problem in taking any real number here in place of x. And what is the output? The output is c, which is not changing. Here it's changing for every input, here it's not changing. And that is why this constant nature allows us to, it gives us this name constant function. Fine, so there is no problem in choosing any x from R. So R is the domain. But for every x, are we getting a single output? Yes, for a given x, we are getting only C and nothing else. It's a different matter that for many x, in fact all x, we are getting the same C. But that's not a problem. Once you choose an input, for that input only one output should be there. And that's why this is also a function. And because we are having only one output, the range is this singleton set. Now let us see its graph also. Due to the general nature of C, of course you cannot draw the graph simply like that. Let me take 2 values of C and then draw the graph for those 2 values. But simultaneously, say I take C equal to 2 and C equal to minus, these are 2 different cases, okay. Of course, they cannot simultaneously be 2 and minus 1. Just like the graph of the identity function, here also we are going to get straight line graphs. Now, if you make a similar table, say for the value C equal to 2, what will you get? So this time I am going to take 4 values only. Say minus 2, minus 1. It's not necessary that every time you have to take integers only. You can take fractions also if the graph is really complicated, in order to see how it looks. So no matter what my input is, the output now is constantly 2. So if you plot these points in the plane, say this is my minus 1, minus 2, 0, 1, 2, 1, 2. First of all, For minus 2 it's 2, minus 2, 2. So the point is roughly here. For minus 1 also it's 2, minus 1, 2. For 0 also it's 2, 0, 2. For 1 also it's 2. So you get the horizontal line which is parallel to the x-axis 2 units above the x-axis. And again, because I have done it so carelessly, the points likely will not lie on this line, but you can imagine that this is the graph. In a similar manner, if you take c equal to minus 1, then the graph will be the horizontal line 1 unit below the x-axis. So for constant functions, the graphs are all going to be horizontal lines, and their positions will depend on the actual value of the constant. Next comes the class of polynomial functions. Let the function f from R into R, again a real function, be defined by this formula. At the input x, the output looks like this: an x to the power n plus an minus 1 x to the power n minus 1, plus, let me write one more term, an minus 2 x to the power n minus 2. So like that it goes. Following that pattern, we will eventually reach a2 x square, because these exponents are gradually decreasing one by one. Every time we write an exponent, it's one less than the previous one. And similarly, the suffix values also are that. a1x plus a0 a0, where n is a non-negative integer and these coefficients are all real numbers. N minus 2, an minus 1, an, these are real numbers. Okay, so the function formula here is much more complicated than our constant function and identity function. But if the formula looks like this, where n is a non-negative integer and these are called coefficients, you already know these things. They are all real numbers. Then f is said to be a polynomial function. The prefix poly denotes many. That means there are many terms which look like this. Each individual term is a power of x multiplied by some real number, and those real numbers are coefficients, and all those terms are added together. That is the formula for f of x. Now note one thing. Note that since n is, this is important to note. We understand that all the coefficients should be real numbers. But what is this condition? N is a non-negative integer. That means n is not negative, but n can be 0 or n is positive. So the smallest value of n is 0, is a non-negative integer we can have n equal to 0. In that case, obviously the formula will not be so complicated because n is 0. What will you get if you put n equal to 0 here? X to the power 0 becomes 1. an becomes a naught. And the other terms that you see in this sum are actually not there. This is just a symbolic way of writing the entire thing. Okay, it does not mean that every time for every n you are always going to get n minus 1. These terms and the fact that we write dot 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 simply indicates that if there is room for such terms, then they are going to look like this. But if there is no reason for these intermediate terms to exist, they are not there. For example, when n is 0, this first term actually becomes nothing but this itself. So the other terms actually are not there. So in this case, f of x is nothing but a0. And a0 is a fixed real number. You can choose a0, but once you choose a0, then it will not change with x. And that is why this is a constant function. So f is a constant function. This tells us that constant functions actually are also polynomial functions, special types of polynomial functions. Let us see one more thing. Also, note that when this n as well as all these a's are our choice, right? So we can take special values of these quantities. Let me take n equal to 1, okay. a0 equal to 0 and a1 equal to 1. Then, I wrapped this up. No, let me just again write it, the general polynomial, so that you can see what is going on. So what we have taken, n is 2. That means if you start from this side, you have a naught, you have a1x and you have a2x square. This itself becomes this. That means the polynomial function has only 3 terms in this sum. Oh, no, what the hell am I saying? Now n is 1, so this term also will not be there. This itself becomes this. Yeah, that is not correct. This itself becomes this, and we have this term. So there are only 2 terms in this sum. However, additionally we have chosen a0 to be 0 and a1 to be 1. That means f of x becomes 1 times x plus 0, which is equal to x. So this is nothing but the identity function. So the identity function on R is also a polynomial function. That means the first 2 examples are special cases of this third one. So you can imagine we cannot draw the graph of a general polynomial function. It will all depend on what the function actually is. But here are some other examples of polynomial functions other than the identity and constant functions. Some polynomial functions are this, say f of x equal to, you can take many examples but these ones are given in the text, x cubed minus x square plus 2. In this polynomial function, if you look at the general formula, a0 is 2, a1 is 0, a2 is minus 1 and a3 is 1 and n is equal to 3. Then another one, g of x equal to x to the power 4 plus square root of 2. Square root of 2 has been taken purposely here just to show that although we are saying the coefficients are real numbers, but the examples so far we have taken have all the coefficients integers. So they can be rational numbers also and even irrational numbers. In this case, a0 is square root of 2, a1, a2, a3 are all 0 and a4 is 1. But the function, and in all these functions, the domain and codomain are R. I am coming back to that issue of whether these are really functions or not. Okay, but before that, let us see a non-example. But the function hx equal to x to the power 2 over 3 plus 2x is not a polynomial. Why? Because this exponent is not a non-negative integer, it's a rational number but it's not an integer. That is why, although this will be a function but it's not a polynomial function. Let us now come to that issue of whether this complicated formula really defines a function. Again, the domain is R. So from R, if I choose an x, in other words, if x is a real number, will there be any problem in substituting any real value of x here? No, because you can calculate the powers that you see of x here, multiply them by these a's and take the sum of those products. You will have no problem in doing that. And for a given x, you are going to get only one output. It looks complicated in this format, but after doing the calculation, you will get only one output. So yes, this is a legitimate function whose domain is R. Range, however, we cannot say. In general, we cannot say. It will depend entirely on this n and the values of the coefficients. So let us next see another example, and this time we have to draw the graph of a polynomial function. Consider the polynomial function f from R to R given by f of x equal to x squared. So here a0 and a1 are both 0 and a2 is 1 and n is also 2. So what we have to do here, complete the table below by using this table. Okay. Using this definition, what else? What are the domain and range? Anything else? I don't see drawing graph, but we will do it. Also, draw the graph, and now we need the table. The table, of course, we will complete here itself. There is no point again making another table. There are quite a few values, -4, -3, -2. Oh, okay. -4, -3, -2, -1, 0, 1, 2, 3, 4. So these are our input x and these are our outputs, which are going to be x squared. -4, -3, -2, -1, 0, 1, 2, 3, 4. So squares of minus 4 and 4 are both 16. For minus 3 and 3 it's 9. For minus 2 and 2 it's 4. For minus 1 and 1 it's 1 and the square of 0 is 0. Okay, so we have got many points with these coordinates minus 4, 16, minus 3, 9 and so on. Now next comes the issue of what the domain and range are. Well, domain of course is R. The domain is R. Again, because either it's given here or the fact that there is no problem in squaring any real number. You can do that to any real number. That will again give you a unique real number, which is in fact the reason why this is a function in the first place. But next comes the issue of finding out the range. Well, the range is the set of all outputs. What can we say about the range? Let me write like this. Range is the set of all outputs. That means all x squares. The collection of all x squares as x varies over the set of real numbers. Now, what type of numbers can appear there? You see, we know one thing about squaring real numbers. If x is a real number, then its square is greater than or equal to 0. In other words, it's non-negative, it's not negative, but it can be 0 only in one case, when x is 0. For other non-zero numbers, whether they are positive or negative, square is always positive. You can see that here. For 4 and minus 4, square is 16. The squares are all positive except one square, which is 0. 0 of course is not positive, it's just 0. And that is why x square is always greater than or equal to 0. This means what? Since these x squares form the range, so the range has non-negative real numbers as its elements. In other words, the range is a subset. Oh, we are not using this symbol here. The range is a subset of the set of non-negative real numbers. And the set of non-negative real numbers is denoted like this. If you go back to set theory and see there how we defined intervals. This is the set of all real numbers that are greater than or equal to 0. But can we say that this is not just a subset of this but actually equal to this? Yes, that is true. But for that you also have to show that any element here also belongs to this set. How can you do that? Let me just take any element y here. This means what? This means that y is a non-negative real number. And for such real numbers, we know something, that its square root exists. Negative numbers do not have square roots. Well, they have, but those are complex numbers. And we are not going to discuss that right now. Non-negative real numbers have square roots, which are also themselves non-negative real numbers. There is a negative square root also, but here I am talking about non-negative square root, which is denoted by that symbol. We know that it exists, although at this moment you cannot really prove that it exists. That is something for which you have to wait. Unless you see a very specific property of real numbers, you won't be exactly able to prove that this thing exists, which is something we do not have to bother about at this stage. We just take it for granted that when y is non-negative, something like square root of y exists, which is also non-negative. It's a real number after all. Its non-negativity is not an issue right now, such that what type of number is it? Its square is equal to y. So from this last equation, what can you say? You see that we have expressed y as something square, and that something belongs to R. Something square and that something belongs to R. This means that y actually belongs to the range. And so, just like the range is a subset of this is also a subset of the range, because that arbitrary element y is also in the range. Therefore, the range is equal to the set of non-negative real numbers. This type of determination of range looks somewhat complicated, but it is what it is. You are not always going to get a situation so easy that just by looking at the function you are able to write the range. You may ask, of course, that simply from this look of the range, how was I able to guess that it should be equal to this? Well, there is no clear-cut answer to that. It's just that I have learned it from somewhere. So the more experience you have with these things, the more you will be able to guess. Okay, so this is the range and this is the domain. Next comes the task of drawing the graph. We will not, of course, use all these points because these are really big for this small space. We will roughly only consider, say, 5 points, plot them, and then we will join them. Five points I am saying. Yeah, okay. 1 point is, let me write the coordinates themselves, 0, 0. Okay. Another point is 1, 1. Roughly, I just put some points here, say 1, 2, 3, 4. On this side also, 1, 2, 3, 4. On the y-axis also, 1, 2, 3, 4. 1, 2, 3, 4. And then we have 1, 1. So 1, 1 is here. But we also have minus 1, 1. Minus 1, 1. 2, 4. When you have 2, the output is 4. Already it has gone quite high. For minus 2 also it's 4. So this time it's not a straight line, but it is something like this. This is the problem of freehand drawing, especially when you are doing it on board. Yeah, it doesn't look nice, but you can just imagine the general shape. It looks like a cup. The graph, of course, doesn't stop here. It extends indefinitely like this, and on this side also it extends indefinitely. But because of the nature of the function, it's as if something is coming along this curve. It crosses the origin and then goes back like that. This is called a parabola, this shape. There are other parabolas also, this is one of them. This curve arises when you throw a stone. That trajectory is parabolic. Okay, so this is the graph of the function y equal to x square. You see, there are many things when we do some such things at this level. No, there are many questions that may arise. How do I know that? See, you just look at this table, you see that we have plotted only a few points. Even if you plot all these points, that's only a few points, that's it. Now, how do I know that in between these 2 points, say 0, 0 and 1, 1? How do I know that the graph has to be like this and not something like this? Say it comes here and this is 0, 0, this is 1, 1. It's not like this. Someone may ask this question, no, what is the guarantee that the graph is like this and not something like this, and then maybe then it goes like that? Because we do not have these values in between 0 and 1. You can plot more, you can take more points, of course, but how many will you take? And even if you take, say, 100 points in between 0 and 1, what about those in between those points? There also the graph may fluctuate, right? So how do we in fact know? We cannot, of course, draw all possible points, but then how do we know that the graph looks like this? This is a question that cannot be answered now itself. It can be answered only when you know calculus. But that's just the example. And then we have an even larger class than polynomial functions, namely the class of rational functions. So let's see them next. Another question may arise here. Say someone adamantly makes a statement that no, what are you doing? You are taking only a few points and you are claiming that the graph is in one piece. I am telling you that the graph actually is broken somewhere. It's not a continuous curve. How will you refute that claim? Okay, such questions will be handled in calculus. Number 4. Rational functions. A real function. Whenever we say a real function, that means the outputs should be real numbers. In other words, the range should be a subset of the set of real numbers, and the domain should also be a subset of R. A real function h, let me call it h, of the form. Of the form means whose rule or formula is going to look like this: f of x divided by g of x, where f and g are polynomial functions. From polynomial functions means from R to R, of course, from R to R is called a rational function. In other words, a function whose formula is some polynomial function divided by another polynomial function is called a rational function. You see, for a polynomial function, no matter how complicated its formula is, the domain is always R, because in that formula there is no problem in putting just about any real number in place of x. It will give you an output value. Here, however, there is a problem. You cannot put in place of x just about any real number. Why? Because sometimes polynomial function values become 0 also. Let me give you an example. Say you consider this polynomial function gx equal to x square minus 1. This is a polynomial function. Here n is 2, a0 is minus 1, a1 is 0 and a2 is 1. However, g of minus 1 is 0 and g of 1 is also 0. So, if your rational function h is this, h of x equal to, say, my f of x, which you can call the numerator, is x plus 2. This is also a polynomial, but the denominator is gx is x square minus 1. For this h, the domain is not R. You will have problem in calculating h of minus 1 and h of 1, because for those values the denominator becomes 0 and you cannot divide by 0. Well, you can divide by 0, but those are other things, okay, we do not need them right now. In the normal system of real numbers, you cannot divide by 0, and that is why when you consider such rational functions, the domain has to be chosen in such a way that from R we remove those problematic points. Is there any problem in putting some value of x other than minus 1 and 1? No. For example, you can put 2, no problem. The denominator then becomes 3, 2 square minus 1, or you can put, say, minus 5, then it becomes 25 minus 1, 24, no problem. Numerator, of course, anyway does not cause any problem. So, for this specific function, the domain is this. From the set of real numbers, you remove minus 1 and 1. If you want, you can choose a smaller domain, but this is the largest possible set that you can take as domain if the formula for the function is this. And that's why for rational functions, the domain has to be chosen carefully. And range again, of course, because the formula has gotten so complicated, it will entirely depend on the function, what the output values are. Now note that I said another more general class of functions is rational functions. Does that mean that polynomial functions are also rational functions? Yes. This class of functions contains the class of polynomial functions inside of it as a subclass. Why? That's because if you take any polynomial function, you can write it as polynomial f of x divided by this constant function, which is also a polynomial. And that is why any polynomial function is a rational function, just like any integer is a rational number. Okay. And finally, let us consider, shall I consider this today? Let me just continue. Let me just stop here itself, otherwise it will become very big, the video. Let's just discuss the rest of it in the next video. And now before I finish, let me also make a remark about polynomial functions. Why are polynomial functions so important? They are considered really very important. One reason is that they are easy to calculate. You may object, no, they do not look easy. But wait, you haven't seen complicated functions. The kind of functions that really arise outside of mathematics in applications, they are really very complicated. Those functions are important because they arise there, and that's why they are needed. They can be approximated by polynomial functions. Instead of working with them, you can work with some polynomial functions which will not give you the exact value that those functions give you, but these values will be very close to the exact value. The reason why this happens is well beyond our stage right now. So maybe one day you will realize why that is the case, if you go far enough with these things. But with that, I am just going to stop, and tomorrow what do we have? We have linear algebra, no? So that's just it. So see you tomorrow with linear algebra. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.